Hello everyone, welcome to this lesson. So in this lesson, we're going to continue our discussion on ordinary differential equations, more specifically, improvements on Euler's method. Now, if you remember from the last lesson, we have discussed that Euler's method uses linear extrapolation to get yi plus 1 using yi plus the derivative at yi multiplied by h. We have also described that this is actually linear extrapolation. Basically, if we use an example of the initial condition here 2, it uses 2, the derivative at 2 to get the second point, uses the same information on this point to get the third point, then the fourth point, and so on. In this lesson, I'm going to be introducing a new ordinary differential equation, dy dx sine t squared multiplied by y, with an initial condition y equal to 2 at x equal to 0. Now again, solving ordinary differential equations involves using only those two pieces of information, the derivative and the initial condition, to create a trajectory that describes the original function or the exact solution as you see down here. Now, one thing I want to mention about Euler's method is that when we are taking, say, for instance, this initial point 2 and taking a derivative at this point to describe this point, what we're doing here is we're taking the derivative at the start of the interval to be a representative of how the derivative is changing throughout the entire interval. Now, this can be fine if the interval is linear, but if the interval has a lot of curvature, doing this can actually yield a lot of error. So improvements on Euler's method imply improvements on the derivative approximation. In other words, how are we going to describe how the derivative is changing throughout each one of these intervals? So if you look at Heuns' method, for example, it takes the derivative at the start of the interval plus the derivative at the end of the interval divided by 2 as a good representation of how the derivative is changing in each one of these intervals. If we look at the midpoint method, it uses the derivative at the midpoint of the interval to be a good representation of how the derivative is changing in each one of these intervals. Ralston, on the other hand, uses a weighted average. It gives 1/3 weight to the derivative at the start of the interval, 2/3 to the derivative at 3/4 of the interval. And if we add, of course, 1/3 to 2/3, it adds up to 1. So in this lesson, we're going to actually see how these are in fact an improvement on Euler's method just by simply creating a better approximation for the derivative of each one of these intervals. So let's actually begin. So before I actually go into Heuns, Midpoint, and Ralston, I would like to review Euler's method briefly. If you remember, Euler's method is a linear extrapolation. yi plus 1 is equal to yi plus the derivative at the start of the interval multiplied by h. Now, if I apply this equation to each one of these intervals, an interval here has a width of 0.5. I'm going to get the following numbers. Now, if I graph them here to see how they describe the exact solution, we can see that it describes very, very nicely the trend of the function. But of course, as we see the white space between these two curves, Euler's method still incurs error when it comes to using 0.5. Now in this lesson, I'm actually going to keep the step size constant at 0.5 to describe all of these 4 techniques. Here's how Euler's method performed. So in the next slide, let's actually see how Heuns' method would perform. Now, before I actually go into describing the numbers here in the table and also the graph, I want to actually go through the calculation of Heuns' method. The reason that is because if you look here, we have yi, we have phi, and we have h very similarly to the Euler's method. But we here also have phi plus 1. Now, to get the derivative at phi plus 1, I need yi plus 1, but we don't have that yet. So what we're going to be doing is we're going to be using Euler's method as the first step to get yi plus 1, or the first estimation of yi plus 1. Then I'm going to be plugging it into this derivative function here. Then I'm going to get phi plus 1, and once I have that, I'm going to be plugging it into this original function to get the yi plus 1 that I'm actually interested in. And so Heuns's method actually requires 3 different calculations for each step size that we're going to go through here. First, uses Euler's method to get yi plus 1, then the second calculation to get the derivative at that point, then takes this derivative and plugs it into this main equation. Now I'm going to go through in more detail the calculation of these numbers, but in this lesson I'm going through the conceptual side of a lot of these techniques before we go into the coding. So if I graph the Heuns, as you can see here, this is the gray line. It's actually a massive improvement on the Euler's method. It almost grazes the true values here. So very, very good improvement. So actually, let's actually go to the midpoint method and see whether or not it's going to be as good of an improvement as Heuns's method. Again, like with Heuns's method, it actually involves 3 different calculations. Since here we are trying to also get the derivative at I plus 1/2, we're going to have to get the y at yi plus 1/2. So we're going to use Euler's method to do that. Simply, the only difference that you do with Euler's method is basically you do it at h divided by 2. This is going to give you yi plus 1/2, and we take this y, plug it into this derivative, will get us the derivative at phi plus 1/2. Then once we have that, we plug it in here. So much like with the Heuns, we have this first step, the Euler's method, then second step, calculation of the derivative at that point, then third step, plugging it into the midpoint method equation. Now, if I apply this 3 equations on each step size, I get here these numbers. And if I graph them, I get this yellow line here, and you can see it's actually almost identically superimposed over the Heuns's method, which gives us almost identical estimation and most definitely improvement on Euler's method. So you can see that actually using a different derivative to describe each one of these intervals yielded a much, much better approximation than simply using the derivative at the start of every interval. So let's actually go through the last and third method of improvements on Euler's method. So much like with the Heuns and the midpoint, also this requires 3 different calculations since we have the derivative at I plus 3/4. So we're going to we're going to use Euler's method. Basically, we're going to be using 3/4 of the step size. This will get us the yi plus 3/4. And using this yi plus 3/4, plug it into this derivative, will get us this phi plus 3/4, and then plug it into this original equation here to get yi plus 1. Now we apply these 3 different calculations at each step size, and we'll get these following numbers. Now, if I graph them, this is the blue line for the Ralston, and you can see it's almost again superimposed to the Heuns and midpoint and give us very similar estimations as the midpoint and Heuns, and also, of course, a massive improvement on the Euler's method. And I do want to remind you, this is just for the step size of 0.5. So you can imagine if we have even a smaller step size, these 3, the Heuns, midpoint, and Ralston, will give us an even better approximation than we have over here. Now, there's one thing that I do want to mention. The reason all 3 of them are actually giving us very similar approximations can be found here. The Euler's method actually describes each one of these intervals using 1 derivative approximation. But if you look at these 3, they use 2 derivative approximations. Here it uses the start and end of the interval. Here it uses the start and the midpoint of the interval. And here it uses the start and the 3/4 of the interval. Now with the midpoint, you can see, we do have only 1 derivative showing here, which is I plus 1/2, but to get that, we actually used the derivative at the start of the interval when we applied the Euler's equation, or the Euler's equation. So you can see this in fact also has 2 derivative approximations in them. Now, in the next lesson, I'm going to be describing how to actually develop codes for the Heuns, midpoint, and Ralston method. And what we're going to be doing essentially is recreating these three tables using the Python code and also recreating this graph. Now, that will be it for this lesson, and I will see you in the next lesson.